Hi, welcome to this video demonstrating cap properties of NoSQL databases using partition tolerance experiments. Let's start with the CP system, MongoDB. Here is a view of my AWS EC2 dashboard for the MongoDB experiments. I am using three EC2 instances, each hosting one member of the MongoDB replica set named priv-A, priv-B, and priv-C. This is MongoPriv-A, the first instance. It has a private IP address. Its security group allows port 22 for SSH and 27017 for MongoDB. The other two instances have a similar config. To access these instances, I use a jump box with a public IP. Now let's have a look at the subnet configuration. Subnet A has a CIDR block of 10.0.3.0/28. Subnet B has .16/28 and Subnet C has .32/28. Each of the three MongoDB instances are deployed in a separate private subnet. Now let us look at the ACLs to understand the partitioning approach. There are three ACLs, one for each private subnet, which deny traffic to or from the other two private subnets. One correction, rule number 2 is supposed to be deny here. Currently, the three restrictive ACLs aren't associated with any subnet. The default ACL is currently associated with all three. This is a Python script that uses PyMongo. It defines functions needed for simulating the experiments. It can be found in the GitHub repository linked in the description. For running these functions, I will use the Python shell running on the jump box. Note its private IP 10.0.0.102. Let's look at the other tabs. First is a Mongo shell on node A and a continuous log of its MongoStat output. Then a shell for node B and its stats, and finally node C and its stats. Let's start the execution with the insert all function. We immediately see the number 15 in the insert count on all the three nodes. The write happens on all three of them. Now to begin experiment 1b, let's set the read preference to primary. I'm verifying that it is properly set using the db.readPreference command. Now let's try a read all and check which node received the reads. We see that the query was directed to the primary and the two secondary nodes did not receive it. Now let's simulate a partition by isolating node B from the others using the restrictive ACL. Now let's issue a series of successive read requests while the partition and leader election is happening. Node A did not receive any queries. Node B received all the queries till it switched from primary to secondary. And Node C started receiving queries after it switched from secondary to primary. Now let's test writes by using the update test1 function. Node A is a secondary node connected to primary. Node B is not in the same partition, so no update is seen. Node C is the primary. Its update count also increases as A. Issuing a read all on the Python shell, we see that the role of one person has been changed. This indicates that the write was successful. All the read queries are now serviced only by node C, which is the new primary. Let's log into node B and query this data. Since it is unconnected, it didn't receive the update and the role of the student Cindy is still the same as before. Let's remove the partition by changing the subnet association back to the default ACL. There it is. Node B received the update as soon as the partition was removed. We can see the updated data. This is also confirmed by an increment in the update and query counts for node B. Let's issue a few more read requests and verify that node C is still the primary, even after B has joined the cluster. This completes experiment 1B, the consistent and partition tolerant system. The next three experiments will involve similar steps, only the results will vary based on the read preference setting. So for experiment 1C, the read preference will be set to primary preferred. Let's isolate node C from the other two. Let's issue a series of reads to understand the behavior during the network partition process. Node A changes from secondary to primary. Node B was a secondary throughout but still received some queries, unlike in experiment 1B. Node C changed from primary to secondary. It got demoted because of the partition. Executing the function update test2, Cindy now gets back the student and staff roles from Eric in our data. The update and query counts increment on node A, which is the primary. The update count increments on node B. There are no updates on node C, the partition secondary. Checking on the local shell of node C, it still has the stale data with Eric having the two roles. Note that the query count has been incremented since we issued a local query. Now let's heal the partition. Now the update has been received on the node C. The reads are still getting service from node A, which is the primary. We can conclude that this is a CP system with a slightly better availability. Now for experiment 1D, let us set the read preference to secondary. Let's verify that node A is the primary and the cluster has all the three nodes. Now let's issue a series of read queries. There are no read queries on the primary, while both the secondaries show non-zero query counters. Let's simulate a partition by taking out the primary node A from the cluster. Let's issue a series of read requests. This time we don't see the reconnect error that we always used to see on doing the partition. Node A started getting read queries after it was moved from primary to secondary. It can be seen from the counters here. Node B got promoted from secondary to primary. So it stopped getting any read queries after it was primary. Well, node C was secondary throughout. Now let's run the update. Node B and C receive the update since they are still part of the cluster. On testing reads, inconsistent data is seen. Both Cindy and Eric are seen to have the student-staff dual role. This is an impossible scenario. Data randomly changes on each subsequent read. Read queries are being directed to node A, which is the unconnected secondary, and this is the culprit. Node A has stale data. Now let's heal the partition and see if this gets corrected. The data on node A just got updated. Now, even after trying on the Mongo shell, we can see consistent data. Thus, we can conclude that this is a partial AP system. There was no downtime reconnect error, but data read after partition might be stale in this case. Now, let's move on to experiment 1E, which sets the read preference to the nearest node. On issuing a series of PyMongo shell reads, we see that the read queries are being serviced by all the three nodes now. Now let's partition the network. Since we have a local cluster in this case, the nearest parameter doesn't mean much, and the queries are as such expected to go on all the three nodes. Um, this fact is seen even after we partition the network. Now let's run the update test 2. Now, on testing the reads, we again see inconsistent data, pointing to the impossible scenario of both Eric and Cindy having the dual role. The read queries are seen on all the three members. So now let's remove the partition and let the cluster heal. Consistent data is now seen on the PyMongo shell. This concludes our MongoDB experiments. Let's move to experiment 2, an AP system, RiakDB. AWS config includes 3 Riak instances and the same jump box we used earlier. All 3 Riak instances are in the same subnet now, 10.0.1.0/24. The jump box has a public IP for remote access. Riak members use Riak AMI offered by the AWS free tier. The cluster is up and running. The config for this is mentioned in GitHub repo. Network partition will be simulated by applying firewall rules on the machines hosting Riak instances. I will use curl for all the data reads and writes. Now, let's use the jump box to write data to the cluster. Let's verify that all the nodes have received this data. Now that we have checked that all the nodes are connected and are receiving the updates, let's create a partition by applying firewall rules on node 1 to drop all the traffic from node 2 and node 3. It takes some time for the cluster to detect this. Now let's update an entry on node 1 and another key on node 3. Let us read the data on node 1 and 3 while the cluster is still in partition state. Stale data is observed, but reads and writes are working on all the three nodes. Let's heal the partition by removing the firewall rules and check the data on all the nodes now. All the nodes now show updated data. Only latest data is retained based on vector clocks, while old copies are deleted. Thus, we conclude that Riak is an AP system with last write win strategy for conflict resolution.